I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to see the topic Scalar and Vector Magnetic Potential for the course Electromagnetic Fields. So we know that in electrostatics there is a potential called scalar electric potential denoted by V, and it is related with electric field intensity E is equal to negative gradient of V, that is E is equal to minus del V. But in case of magnetic potential, there are two types of magnetic potential. One is called scalar magnetic potential denoted by Vm, and another one is vector magnetic potential denoted as A vector. So to define the scalar and vector magnetic potential, we are use two identities which will be listed by the properties of curl. That is del cross del V is equal to 0. Here V is the scalar, and another one equation del dot del cross A is equal to 0. Here A is the vector. So every scalar V and every vector A vector must satisfy these identities, and Vm is denoted as scalar magnetic potential, and this must satisfy the equation del cross del Vm is equal to 0. But the minus del Vm is equal to magnetic field intensity H vector. So by substituting H is equal to minus del Vm in equation 3, this becomes del cross minus H is equal to 0, and we can write del cross of H is equal to 0. But we know that according to Maxwell's equation, del cross H is equal to J. Since del cross H is equal to 0, this J also 0, and the scalar magnetic potential Vm can be defined for source free region when J is the current density is given by H is equal to minus del Vm. This is for J is equal to 0, that is current density 0. And the relation between electric field and the electric scalar potential, the magnetic scalar potential can also be expressed in terms of H as V of m comma b is equal to minus integral over b to a h dot dl. So this is a specified path. And now we are going to see the Laplace equation for scalar magnetic potential. So we know that the magnetic field does not have monopole. So integral over the closed path b dot of d is equal to 0. But according to divergence theorem, this integral over the closed path b dot d is equal to volume integral of del dot b dv, and this is equal to 0. So we can write by removing the integrals, del dot b is equal to 0, but we know that b is the magnetic flux density related with magnetic field intensity as b is equal to mu naught h. So by substituting in del dot b, we can write del dot mu naught h is equal to 0, and also we can write del dot h is equal to 0. By substituting h is equal to minus del Vm, we can write del dot of minus del Vm equal to 0, or del dot of del is del square. So del square of Vm is equal to 0. So this equation is known as Laplace equation for scalar magnetic potential, and this equation we can say that it is similar to the Laplace equation for electric scalar potential del squared V is equal to 0. And now next we are going to see vector magnetic potential. We know that the vector magnetic potential is denoted by A vector, and it is measured by the unit Webers per meter, and it must satisfy the equation del dot del cross A is equal to 0. We know that del cross of A is equal to B, that is magnetic flux density. So we can write the equation del dot of B is equal to 0, where B is equal to del cross of A. And the curl of vector magnetic potential is the flux density, that is del cross of H is equal to J. By substituting H is equal to B by mu naught, we can write del cross of B by mu naught is equal to J, or del cross of B can be written as mu naught into J. This substituting B is equal to del cross A, we can write del cross of A is equal to mu naught H. But we know the vector identity, del cross A is equal to del into del dot A minus del squared A. So by substituting the vector identity on the left side, instead of del cross A, we can write del dot A minus del squared A is equal to mu naught of J. And J can be written as 1 by mu naught del cross A, or is equal to 1 by mu naught del into del dot A minus del squared A. So if the vector magnetic potential is known, then the current density J can be easily obtained from the previous equation. And for defining A, the current density need not to be 0. And now we are going to see the Poisson's equations for magnetic field. It is given as del squared A is equal to mu naught into J, because J is 1 by mu naught into minus del squared A. So from this we can write del squared A is equal to minus mu naught J, and this is known as Poisson equation for magnetic field. And now the vector magnetic potential is defined for various distributions, current distributions. For current element, if it is a differential current element, the vector magnetic potential A can be given as integral of mu naught I dl 4 pi r Weber per meter. This is written according to the Biot-Savart's law, as we seen already. And if it is a surface charge, then we can write A vector is integral over the closed surface mu naught k ds by 4 pi r. Here k ds is K is surface current density. And if it is line integral, and if the volume charge density J is given by ampere per meter square, then IDL can be replaced by JdV, where JdV is the differential volume element. So the magnetic potential A is given as integral over the closed volume mu naught JdV by 4 pi r Weber per meter. And it can be noted that the zero reference for A vector is at infinity. No finite current can produce the contributions as R tends to infinity. And assessment questions: the types of magnetic potential, Laplace equation for scalar magnetic potential, Poisson equation for magnetic field. Thank you.